The work energy theorem is a very powerful tool, and I just want to summarize it to make sure we all have a good understanding of what's going on. So the very first thing I want to do is just review a couple things. First, we have the energy stored in a spring. And the energy stored in a spring is called elastic potential energy. We call it EPE. It is a form of potential energy. It is a form of mechanical energy, so we do need to include it. And remember, we can calculate it. It's 1/2 kx squared, where k is the spring constant. And remember, the spring constant is measured in newtons per meter. Then we have kinetic energy. This is the energy of motion, abbreviated KE, and it is equal to 1/2 mv squared, okay, where v is velocity or speed. Since it is squared, it loses its direction. And then finally, we had gravitational potential energy, and this one you'll see me abbreviate as GPE, gravitational potential energy, and it's equal to mgh, where h is our height above zero. Okay? Now, I'm going to work an example problem that actually takes all three of these things into account, but remember the law of conservation of energy, which says energy cannot be created or destroyed, basically tells us that as long as we don't have anything that's reducing the amount of mechanical energy, like friction changes mechanical energy into thermal energy, that our total mechanical energy stays constant. So total energy stays constant. So let's look at an example problem. Dave jumped off a bridge. Not probably his best move, but hey, he was planning ahead and he tied himself to a bungee cord. So yay, he's not going to die. Sweet. But we want to know, if Dave has a mass of 75 kilograms and he fell for 15 meters before the constant or this cord started to stretch, and it has a spring constant of 50 newtons per meter, how far below the bridge will Dave fall? Now this problem is kind of interesting because it involves all the different forms of energy. So this is my bridge up here, and this is h0 because this is where he started. It's not zero height, it's just where he started. And then 15 meters below that, so h0 minus 15, I have where the spring starts to stretch, and then, I say spring, it's a bungee cord, and then somewhere down here, my h final is actually where he stops and comes back up. And I'm actually trying to find that whole distance. I'm going to do this with the conservation of energy. Up at the top, we have energy. In the middle, we have energy. And at the bottom, we have energy. Now, as long as we can ignore friction, the law of conservation of energy says that all that energy is mechanical, nothing is reducing it, so it's going to stay the same everywhere. So at the top, we have gravitational potential energy plus this energy in the spring, elastic potential energy plus kinetic energy, and that's equal to whatever it is, a constant. It is nice to note that there is no elastic potential energy because the cord hasn't started to stretch, and there is no kinetic energy because he's not in motion yet. At the middle, the gravitational potential energy here plus elastic potential energy here plus kinetic energy here is equal to this same constant. However, at this point, we do have kinetic energy. We still don't have elastic potential energy because this is just the length of the cord. It hasn't started to stretch yet. And our gravitational potential energy has changed. Now, if our kinetic energy increased, our gravitational potential energy decreased, which makes sense because he is now closer to the ground. He fell down. He's got less gravitational potential energy. And these two constants are equal to each other. Finally, at the bottom, we have gravitational potential energy plus elastic potential energy plus kinetic energy is equal to that same constant. That hasn't changed. However, what is different here is our gravitational potential energy. This might be a good place for it to be zero because he's not going to go any lower than this. So this is actually what I'm going to call my zero height. His elastic potential energy, whatever it is at a maximum because he doesn't go any lower. This is the most the spring stretches. And his kinetic energy is back to being zero because he's at his lowest point. He's not going down. He hasn't started to come back up yet. So how are we going to solve this equation so that we know how far down below he actually is at this point? Well, that is why we're going to pick our height here to be zero. So here's what I know. His gravitational potential energy here is at the top is the distance the thing stretched plus 15 more meters. So his gravitational potential energy is his mass times his gravity times his height, which is x plus 15, plus his elastic potential energy, which is 1/2 kx. Whoops, sorry, we're at the top. We're not there yet. So this is at the top. These two terms were 0. So I'm done with his elastic. I'm done with the top energy. So now I'm going to go ahead and I'm going to go to his energy at the bottom. I don't care about his energy at the middle. Doesn't matter to me at all. It's not going to help me solve for how low he goes. I just want to know where he's at the bottom of this. So this is all of the energy he had originally was all potential energy. At the bottom, it's all elastic potential energy because he's not moving anymore. We could figure out how far he's or how fast he's going at that point if we wanted, but it's irrelevant to the problem. All right. So this is equal to 1/2 kx squared. This is where we have the spring constant and it's all elastic potential energy. So since I established my 0 as this, I know all this stuff. I know Dave has a mass of 75 kilograms. It told us in the problem. I know G is 9.8. I don't know X, but I can hopefully solve for it. And this is equal to 1/2. It told us the spring constant was 50. And again, I don't know X. I'm trying to solve for it. So I'm going to go ahead and grab my calculator, and we'll see if we can get some of these numbers taken care of so we can get this problem solved. So here's my calculator. Clear all that junk out of it. 7.5 times 9.8, enter. 73.5 x plus 15 equals 25x squared. And then we'll do a little bit more math here. 73.5 x plus, if I distribute that 73.5 times the 15, 73.5 times not 11 but 15 is 1102.5, and that's equal to 25x squared. So now all I have left to do is solve for x, and you'll notice it's a quadratic because of that spring constant. So I'm going to go ahead and subtract everything over. So I have 25x squared minus 73.5x minus 1102.5 equals 0. And one more time with our calculator, program quadratic, go. 25 for A, negative 73.5 for B, and negative 1102.5 for C. Alright, we get two terms. We get 8.27 and we get negative 5.33. Which one is the one we want? We actually want that positive term because we set up our x to be a positive distance, x plus 15 to get our top. So that 8.33 meters is how far that bungee cord is going to stretch before Dave comes to a rest. Then he'll spring back up and oscillate a little bit. Okay? So that is a problem that involved all of the energy equations that we needed, and we had to choose our 0 gravitational potential energy carefully.